Okay, so here we've got the notes for Unit 3, Sections 1 and 2. So just the review preview up here at the top. Here's what we're looking at, using real sample data or use probabilities to find the results that are expected. So obviously, sometimes it's not efficient to, throw a die 100 times. You can use probability to generate your results. Okay, so Section 2, probability distributions. So basic concepts for a probability distribution. So you have a random variable, usually x, that has a single numerical value determined by chance for each outcome of a procedure. So your results are numbers. Probability distribution is a description that gives the probability for each value of the random variable, table, formula, or a graph. So like a histogram or something like that. A discrete random variable has a collection of values that is finite or countable. So for example, dice rolls can be 1, 2, 3, 4, 5, 6. That's a discrete random variable. A continuous random variable has infinite and many values. That's not countable. So for example, heights. No, that's continuous. There's people who are between 5'10" and 5'11". Like you can be 5'10" and a half, you can be 5'10" and 3/4, so on and so forth. So it is a continuous random variable. All right, probability distributions are the requirements for them. There's these three things must be true. There's a numerical random variable x, and its values are associated with probabilities. Second rule, the sum of all the probabilities has to be 1, where x assumes all possible values. Now, sometimes you'll get 0.999 or 1.001 simply because we've made some rounding errors, but 2 is definitely not right. 0.5, no. So it needs to be real close to 1. And the last one, the probability of each individual event has to be between 0 and 1. So remember, probabilities can't be negative. It can't be more than 1. Probability of 0 is the event doesn't happen. Never, it's impossible. A probability of 1 is the event is guaranteed to happen. So between 0 and 1, inclusive means it could equal 1 or, equal 0 or equal 1. Okay, so turn the page over here. Some notation, which has come up previously. Sometimes we'll use 0 plus to represent a probability value that is positive, but very small, so highly, highly unlikely, such as this value, 0.10000000123. So if you rounded and just said 0, that's a little misleading because in probability, 0 means the thing cannot happen ever, no matter what. But this is possible, just really, really, really unlikely. So that's just some notation. So example 1, in a research center poll, subjects were asked if the use of marijuana should be made legal. The results for that poll were used to create the table below. This table 1 describes a probability distribution. So rules for probability distribution, random variable that is numerical in nature, probabilities have to add up to 1, and the probabilities have to be between 0 and 1. So this one, right off the bat, is no. These are not numbers. Yes, no, I don't know. So this is not a probability distribution. So the variables are not numbers, they are phrases. Is not a number. Okay, so example 2. Executives were asked for job applicants should discuss salary. Table 2 is based on response. Does table 2 describe a probability distribution? So here's our variables, here's their probabilities. So the rules are variables all add up, or are numbers. So yes, criteria 1 is met. Option 2, the sum of the probabilities has to add up to 1. So let's check that out. If I add these numbers up, 0 plus 6 plus 0, that's 6. 3 plus 2 plus 1 is 6. So that number is not 1. No. The sum of the probabilities does not equal 1, like it should. Okay, example 3. Does P of x equal x over 3, where x can be 0, 1, or 2? Determine a probability distribution. So our table would be 0, 1, 2, 0, 1/3, 2/3. So this would be our x column. This would be our P of x column. So criteria 1 are x's numbers. Yes. Probably, or thing 2, does P of x add up to 1? Well, 0 plus 1/3 plus 2/3, that's 3/3 or 1. So it's good there. And the third one is, are the probabilities between 0 and 1? Yes, they are. So yes, this one is. Yes, a probability distribution. So there you go. 2, all right, whoops, lost my papers. Page 3. parameters of a probability distribution. So, with a probability distribution, we have a distribution of population instead of a sample. So the values of, oh dear, did none of my equations print? Oh, they did not. So I'm gonna have to copy them down. Mean for a probability distribution looks like this. This is gonna be fun. So it's mu equals the sum of x times p of x. So to find the average for a probability distribution, you multiply each value by its probability and add them all up. Variance for a probability distribution. So we've got sigma squared as variance equals the sum of x value minus its average squared times the probability of x. Or sigma squared equals the sum of x squared times p of x minus the average squared. This one's probably easier to use if you are doing a manual calculation. And then the standard deviation is just the square root of the variance, so the square root of the sum of each value squared times its probability minus the average squared. There you go. So, I wonder why those didn't print. All right, expected value. So the expected value of a random variable is denoted by E, and it's the mean value, and it is the mean value outcome. So E equals mu, and E can be found using this same formula. So example 4, table 3 describes the probability distribution for the number of girls in 2 births. Find the mean, the variance, and the standard deviation of the probability distribution. So to find the mean, that's the sum of each x value times its probability. So 0 times 0.25 plus 1 times 0.5 plus 2 times 0.25. So that's 0 plus 0.5 plus 0.5 equals 1. So the average value is 1. So the variance is equal to the sum of each value squared times its probability. So 0 squared times 0.25 plus 1 squared times 0.5 plus 2 squared times 0.25, and all of that minus the average squared. So this is 0 plus 0.5 plus 1 minus 1. So the whole thing, the variance is 0.5. The last thing, the standard deviation, that's just sigma, which is the square root of the variance. So we'll call that about 0.7. So why not? So there you go. That's how you do it using these lovely formulas. Okay. Okay. So over here, so range rule of thumb. So we've actually talked about this before. The maximum usual value is the average plus 2 standard deviations. The minimum usual value is the average minus 2 standard deviations. So it says in example 4, we found that for families of 2 children, the mean number of girls is 1 and the standard deviation is 0.7. Use these results in the range rule of thumb to find the maximum and minimum usual values for the number of girls. Based on the results, if a couple has 2 children, is 2 girls unusually high or unusually low? So maximum is equal to the average plus 2 sigma, which is 1 plus 2 times 0.7, which is 1 plus 1.4, which is 2.4. The minimum is the average minus 2 standard deviations, so 1 minus 2 times 0.7, 1 minus 1.4, which comes out to be negative 0.4, which doesn't make a whole lot of sense because you can't have negative kids. Doesn't work out that way. So this should actually technically be 0, but mathematically it comes out goofy. Now, is this number unusual? No. Simply because the maximum usual value is 2.4, and 2 is not more than that. So it falls within that range, so it's not an unusual number. Unusual numbers have to fall outside that range. A number less than 0, can't have negative people, or more than 2.4, which means you have to be 3 or higher, so you can't have fractional people either. Okay, so probabilities determine when results are unusual. So unusually high numbers of successes, X successes among N trials is an unusually high number of successes if the probability of X or more successes is unlikely with 0.05. So I think delete my, it did. There's some stuff that should be in here. So P of X or more is less than or equal to 0.05. And this one, same thing, P, X or fewer, less than or equal to 0.05. So essentially if it has less than a 5% chance of happening, it is unlikely or unusual probability-wise. All right, so 6, you got here the X sort, produced 879 girls and 945 births. Is 879 girls and 945 births unusually high number of girls? What does it suggest about the effectiveness? So, what you've got here, let's see, is it unusually high or more girls? Now, the thing is, this is highly unlikely because you'd expect it to be very close to 0. The mathematics we're not going to worry about just quite yet because it'd take a lot of essentially fractions. You'd have 1/2 to the 945th power, which would be really 0. So the probability of 879 or more, you should say. So it's essentially 0. We'll put a little plus sign after it because it is possible, but not. So this is very unusual. The probability is less than 0.5. So it is effective because that's an unusual result to get. Okay, and I believe brings us to the last thing for this section, expected value and decision theory. So the expected value is essentially the average. As we talked about that before. So you have $5 to place on a bet in the Golden Nugget Casino. You have narrowed your choice to one of 2 bets. So roulette, you're going to bet on the number 7. Craps, you're going to bet on the pass line. So if you bet $5 on the number 7 in roulette, the probability of losing $5 is 37/38, and probably of making a net gain of $175 is 1/38. So that's how much you'll make back. Find your expected value if you bet $5 on the number 7, and then same thing down here. So event 1, you're going to lose $5. The probability of that is 37/38. The other option is you gain $175. The probability of that occurring is 1/38. So the expected value, the average, is value times probability added up. So the expected value is -5 times 37/38 plus 175 times 1/38. So calculator says -5 times 37/38 plus 175 times 1/38. And that comes out to be negative 0.26. So you're going to lose, your expected result is to lose 26 cents. So the house goes up 26 cents. So down here, same thing, bet $5 on the pass line, game of craps, probably losing $5, so -5, and the likelihood is 251 over 495. Net gain of $5, so $5 is 244 out of 495. Find your expected value. So the expected value is the event times its probability plus the other event times its probability. So this is going to equal, let's see, -5 times 251 over 495 plus 5 times 244 over 495. So that is the decimal, negative 0.07. So you're going to lose 7 cents playing craps. So if you notice, in both cases, you lose. So bets is better. Craps is better because your expected value is less bad. Neither of them are good. You're not expected to win. This is why casinos stay in business. It's because they are, the expected result of any bet is that the casino gets money, not you. Which brings us to the end of this section.